In this video I'm going to be covering the issues that I've come across with the Dometic rooftop heat pump. This generally goes by the model B32XX. I think in my case it's a B3242, but dependent on those last couple of digits you can have inbuilt heaters and other options for them. What's going to be covered in this video is two failure modes, one of which is where the aircon starts reducing its heat output on a cold night, and this is caused by the rooftop coil icing up and the de-icing circuit not working as it should. The other major problem that's going to cover is intermittent operation of the aircon in cooling mode, whereby the compressor essentially comes on and off, and in doing so basically you get vastly reduced cooling output, pretty much down to 50% of what it's capable of. And a lot of this will come back to replacement of electronic devices called thermistors, and so we'll cover that off along with doing some custom modifications to them to make them work, and also doing replacements of thermistors where you can't get the correct thermistor easily. What we've got here is a Dometic 3242 unit, and it's been going this is New Zealand winter time for about an hour and a half, and trying to get the motorhome up to temperature. The air temperature coming out is warm but not as hot as I normally expect it to be, and if you're suffering from this problem, the most likely scenario is that your coil on the top of the motorhome, the outdoor unit, is frosting over. Let's just go and have a look. Now, sure enough, if we have a look at the outdoor unit, the most visible part of the coil is on this side here, and you can see there's a wall of white where we should be able to see aluminium fins, and also down the side as well. So what you can see here is just a solid block of ice, which pretty well extends all the way around the unit. Now on this evaporator coil we have a temperature sensor which is attached to the tubing of this coil near the top, and it's that white cylindrical piece you see there, and what it's supposed to do is pick up the temperature, and if it detects that this has gone below freezing, essentially go through a defrost cycle. That isn't occurring, so there's one of two possibilities. This unit here is stuffed and just not working at all, or the other possibility is that it's just not registering a low enough temperature to trigger the defrost cycle. What I've done here is attach the thermistor up to a multimeter and put it into resistance mode so I can see the resistance reading, and for this particular unit it should be at 25 degrees Celsius, reading about 5 kilo ohms. So the first test I'm going to do is just hold it with my hand, and with these thermistors, they're negative temperature coefficient thermistors, so the resistance should go down as it heats up. So I'll just hold it with my hands and just check that it goes down, and indeed it is. So the next test really is to actually check whether or not it is actually reading the right resistance value at 25 degrees Celsius. So you could get a cup of warm water or something. In this particular case I've got a second multimeter which I can put into temper mode, and this has a thermocouple on the end of it, and we'll just see what sort of temperature my cup of coffee is. Okay, we'll call it 43 degrees Celsius. So if this is put in here, we should get below 5 kilo ohms reading. So we'll go back to the resistance, pop that in to the cup of coffee, and we need to get below 5 kilo ohms because the 5 kilo ohms is at 25 degrees Celsius. So just to be a bit more accurate, I've mixed some hot and cold water together until my thermistor reads around about 25 degrees Celsius. So we're just going to do that check to see whether its nominal resistance is as it should be. Okay, we'll call that 25, and then we'll plonk that in and see what we get. We should be getting 5 kilo ohms. So where we've got to is about 4.76 kilo ohms as a result of being at 25 degrees Celsius. Now what I've done is added a little bit of salt with ice and water into a cup, just so that we can get pity down close to 0 degrees. And what I've got here is currently reading 1 degrees and near enough 15.2 kilo ohms, which is what we would expect as the temperatures drop, so the resistance has gone. Now, given I've removed the thermistor outside and flicked the power back on, you'll see on the display here you get an E4, and that is normal. That indicates that it's seeing an error on the rooftop thermistor. It doesn't believe it's there. So where we've got to is that we've done some basic thermistor tests, one of which involved me holding the thermistor in my hand and monitoring the resistance. Now when you're doing this, you do need to pay attention to the resistance value, because you want to see it constantly decreasing in a nice orderly fashion. I have come across a couple of occasions with thermistors for other projects where that resistance value sort of goes down erratically, and in those cases it was always a repeatable scenario every time I did the test, with no loose connections that I could identify. So you do seem to get a situation where internally within the thermistor something has fractured, or I'm not quite sure what the failure mode is, but the thermistor is essentially no longer reliable. So in those cases you are going to have to replace the thermistor. Now with this particular thermistor, it started life off at 5.05 kilo ohms, so 5050 ohms, and has basically dropped when at 25 degrees Celsius to 4.76, so near enough a drop of 300 ohms. Now thermistors are non-linear devices, so what that means is that at 25 degrees Celsius the 300 ohm difference will actually become something quite a bit larger when we're talking about doing a temperature measurement at 0 degrees. And in fact, as we'll see after I've done a bit of analysis in a minute, it's closer to 850 ohms. So just be aware of that because of that non-linear relationship. The other thing to be aware of is that the change in resistance of a thermistor is sort of roughly exponential, and different thermistors have different aggressiveness to that exponential curve, and that is essentially determined by that beta value. So when you are changing out thermistors, you do need to match the beta value, which I'll cover a bit later on. Now I could have gone and replaced the thermistor given it was reading low, and that might very well fix the problem. But the reality with thermistors is that if you buy a whole batch of 5 kilo ohm thermistors, they're not all going to be 5 kilo ohms at 25 degrees Celsius. So there's a certain amount of manufacturing tolerance here, and probably in terms of its actual figure you'll get will be somewhere between, say, 4.9 kilo ohms and about 5.1 kilo ohms for a new part. So given that, and also dependent on the difficulty in getting a 5 kilo ohm thermistor, you have two options. One is to replace it if you can readily get access to one with the correct beta coefficient, which I'll cover a bit later on. And the second option, which I will be pursuing in this scenario, is that given the thermistor is largely okay but its resistance has dropped, I'll be putting an adjustable resistor called a potentiometer in series with the thermistor, which allows me to tweak its resistance value that the microprocessor and the air conditioner receives, and in doing so essentially get it back into an operating state. In my particular case, that's been done because access to a 5K thermistor is hard. Okay, so what I've got here is an Excel spreadsheet which is capturing the readings that we took at 25 degrees and 1 degree Celsius of the resistance of the current thermistor, and it is also plotting for a perfect thermistor with a 25 degrees Celsius resistance of 5 kilo ohms, 5,000 ohms, what those two would look like. So what we've got here is, in the yellow boxes, these are the boxes which you can change. The orange boxes are the ones where a calculation has occurred. So what we've got here is at 25 degrees Celsius, as best I could determine, we got 4.76 kilo ohms, so 4,760 ohms. And at 1 degree Celsius, we got 15.2 kilo ohms, so 15,200 ohms. Now, when these three figures are put in here, that will automatically cause this beta value to be determined. Now, with these graphs of the resistance versus temperature, you'll see they're not straight lines, they're basically slightly exponential. And what that beta value determines is the aggressiveness of that exponential slope. So you cannot easily change out a thermistor with one beta value for one which has the same nominal resistance at 25 degrees Celsius for one with a different beta value, because these curves will be different. So the only way you can actually get them to read the same temperature correctly is at 25 degrees Celsius. At any other temperature, the two thermistors will basically read different resistance values if they have different betas. Now, for that thermistor which I have tested, moment you plug in these values, you'll get this calculation, as I said, and it's come back as 3,950. Now, based on past experience with thermistors and other projects, this is one of the most common beta values for thermistors that I come across. In reality, though, the actual range you can expect there is from about 3,300 to 4,900. So if you have from your thermistor a calculated beta outside of that range, it is already a fail for the thermistor, putting aside anything else you might think that's good about it. The second thing is that when you do get a replacement thermistor, you do want to get one which is around about the order of 3,700 on the beta or thereabouts. For the case where we're dealing with both the rooftop coil or the indoor coil, given they're only really detecting a few scenarios with their thermistor, they're not doing an actual temperature measurement like the room thermistor inside the aircon does. They only need to operate at a couple of temperatures really, reasonably reliably, and for the rooftop coil it only really needs to operate at one temperature, and that is the point at which it starts icing up. So you have a situation where you can optimize the thermistor that you do have to work correctly with the rooftop coil, because you're only really having to optimize it for 0 degrees Celsius or a temperature around there. So what we've got here is that these values here, based on these numbers here and the calculated beta, are what the thermistor should provide at various temperatures from -10 to 48 degrees Celsius. Over here is a column which represents the actual resistance reading of a ideal thermistor, and what you'll see here is that in the case of where the zero temperature is, which is the significant temperature for the rooftop coil, I've actually got a difference here between the ideal and my thermistor of 808 ohms. So what I've got up here is a box which you can enter a value in, and if I put in 800 ohms, what you will see is these two lines basically intersect. Now they only are going to intersect at 0 degrees. They're still going to be off either side of that, but we're not particularly concerned about that for the rooftop coil. Now what I'm going to do is just put it back to 0 so that you see the difference between my thermistor as it currently is and the ideal one, and you'll just sort of be able to understand what's going on here. At 0 degrees, what we should be getting in terms of resistance is up here, okay? Because we're not getting that with our thermistor, if we draw a horizontal line across here, we'll actually have that resistance value when we get to about -2. So in effect, that 300 ohms, 250 ohms that it's off, is actually causing a temperature misreading of 2 degrees at 0 degrees Celsius. So what I've got in the spreadsheet is a mechanism by where we can put that a fixed resistor in series with it, and if I put an 800 ohm resistor there, you'll see that I can actually marry up the 0 degree point. And if I work out the difference between this resistance value and this one here at any one of these points, and plug that value in, then I'll be able to actually correct it at a different temperature. But the upshot of that is that we need an 800 ohm resistor in series with the thermistor to actually get it to read 0 degrees at 0 degrees. Otherwise it will have to get down to -2 degrees for the thermistor to think it's at 0 degrees. Now I'll make this spreadsheet available in a hyperlink in the notes section of this video. What I've done here is hooked up a 5 kilo ohm potentiometer, which is a variable resistor. This one here is a 30 turn potentiometer, so you can dial it up very accurately. And what I've done is, using a multimeter, determined which two legs will give me a situation where when I turn it clockwise it increases in resistance and anti-clockwise it decreases. I find that very intuitive in terms of adjusting it. So what I've done is connected up a couple of little leads on this, and you see by adjusting this here, the resistance that I'm actually reading I can dial up. Now what I've done is I'm going to set it to about 880 ohms, and the reason for that is that if I set it a little bit higher in resistance, the defrost cycle on the Aircon will kick in earlier than if I set it lower. So this setup will mean that I have some control over how aggressive that defrost cycle is on the Aircon by adjusting this potentiometer. And given I've got it on a couple of fly leads, I can potentially have the Aircon operating, have this outside of the main housing with the cover on so that it gets the proper airflow through the coil, and then actually adjust this until the defrost cycle kicks in. So what you'll see we've got here is the thermistor, and I have cut one side of the wire so that I can insert the potentiometer with heat shrink on and so on. I've put a little bit of heat shrink on the lead that isn't used, so that's not going to contact anything. And in my particular case I've got automotive spade connectors on the end so that this can be easily adjusted. And we've now got a situation whereby when this hits 0 degrees Celsius on the outside coil, the resistance that the microprocessor and the air conditioner sees should be correct in order for it to initiate the defrost cycle. Now while I'm here I might as well just sort of cover off the coil, which is on the indoor side of things. With that side of it, it's basically covered under this polystyrene, and on earlier Aircons of the same sort of size from Dometic, they didn't used to have this polystyrene cover, so that has been put in place in order to improve efficiency, and particularly when you're cooling, so it doesn't lose coldness from inside here to the outside environment. I've taken off a number of screws like that, which you just need a 1/4 inch ratchet for, And there's a number of little plastic clips around here which you release. And then just gently pull up. And you'll gradually be able to get the top cover off. Now there is a bit of sealant over here where various refrigeration tubes come in at the back here, which just sort of needs to be worked a little bit. It's essentially like a blue tack. And then that will just go carefully. Come off. And you'll see what I mean there. The stuff is very, very sticky, and it just helps to seal where those pipes come in. So I'd suggest that you periodically give this a bit of a clean, because while there's filters which stop most of the crap going in here, you'll see there's a bit of crap that is starting to block up the coil, and so you can just get in here and very gently give this a clean. Now you've got a opening here which is where the air's coming through, and of course if you get any water in there it'll fall on electronics as well as fall inside the motorhome. So you do need to be fairly careful cleaning this. You have got a couple of drain ports on either side, so the water will, if it doesn't go outside of this little container here, it will get diverted outside with no problem. So I'll get the hose out and give that a bit of a clean on low pressure and just try to tidy that up a little bit. We're back here at the outdoor Aircon, and I've cable tied the thermistor back on again. Got a bit of insulation tape over the two automotive connectors, and I've run the cables behind the foam here down here, so that I actually have access to the potentiometer and can actually make that adjustment. Now once I'm sort of happy with operation and at the temperature at which it does the defrost cycle, I can potentially hide that potentiometer a bit more inside the Aircon unit so it's out of the weather. Okay, so that coil has been cleaned and everything is looking quite nice. You'll want to clean out the channels in here where dust, and particularly over here where there's a drain hole, spiders can get in there, and another drain hole over here, so even if the motorhome is or caravan is on a bit of a slope, it will drain out of one of those holes. So just get a small paintbrush in there and make sure you've got cobwebs and crap out. Now when you put this back on, these two pieces here need to slide down quite carefully, and you'll see there's a couple bits there for it to slide into these flanges on each side. So just make sure that you line this up nicely so that you don't damage anything here. Now just before I do this, I'll just show you something else. Over here you'll see the thermistors for the indoor unit, and what you're actually seeing there is the top of two thermistors So there's two cables coming out. So this thermistor here has also given up the ghost a couple of years ago, and in New Zealand it was only easily possible to get 10 kilo ohm thermistors. So what I've done here is connected two of them up and put them in parallel to in effect act as a 5 kilo ohm thermistor. And hey presto, after about an hour and a half of running, we now have a defrost cycle occurring. And sure enough, we're in need of a defrost cycle that is pretty much as it was previously, but now it's actually kicking in. You can see it through solid block of ice. So I could potentially set the resistor a bit higher to kick that in a bit earlier, but I might do that later on. Pretty well defrosted already. Now, while this defrost cycle is on, the main difference you'll notice compared to either the heating or cooling is that there is no fan. If the fan was switched on, it would be blowing cold air from the inside coil, because that's getting cold in order for the outside one to get hot inside. So when this has finished defrosting, it will switch off and just let the gas pressures level off after about 2 minutes, and then it will switch back into heating mode, but it won't switch the fan on until it's got that indoor coil back up to above room temperature. Okay, so that's just switched off after having done its defrost, and we just got to wait. So that noise you can hear is just the compressor having switched to operation in the opposite direction. Well, it hasn't switched, but the valves and the aircon have switched the refrigerant flow around. So once that gets the indoor coil up to temperature, the fan will kick in. And there you have it. Okay, so what we've achieved there is a fairly thorough analysis of the aircon not defrosting and causing poor heating performance. You've also seen how to get to the indoor coil and clean it, and also using two 10k ohm resistors, thermistors on the indoor coil to simulate a 5k ohm thermistor. That perhaps worthwhile me just mentioning some of the issues that I've had with this aircon. When I purchased it new, within the first 3 years, probably about a year and a half in, I had a situation where the aircon was in cooling mode, and what would happen is it would put out cold air for about 3 to 6 minutes, and then the airflow would still occur, but the air wasn't cold anymore, and then it would start getting cold again. So it was basically 3 to 6 minutes of cooling and then about 3 minutes of just air coming out with no cooling and then flick back on again. Because I have a watt-hour meter attached to the motorhome, I could see that something was flicking on and off, and indeed there was the compressor, which I could verify by turning the fan speed down. And the other characteristic of this problem is that those timings I've just mentioned were at full fan speed. If you reduce the fan speed, the cycling sort of happens quicker. And what had happened in this particular scenario is that the thermistor associated with the indoor coil had gone bad. It was reporting that the indoor coil was frosting up, and therefore in this particular scenario what happens is that rather than go through a heating process like what I've already documented for the outdoor coil, what this Aircon appears to do is just turn off the compressor so the indoor coil is no longer cooling, keeps the fan going, and by sucking in the hopefully warmer air in the motorhome and passing it through the coil, get rid of the frost development situation that way. So the upshot of that is that when that was taken in, the people working on it had exactly the same problem as I've identified, which was sourcing a 5k ohm thermistor, and in the end I believe they managed to salvage one off an old fridge in order to get it working again. The other experience I've had with thermistors seems to indicate that those that are encased in a metal case, like what you saw with that indoor coil, where I had two in parallel there of 10 kilo ohms, those seem to last longer than the ones which are plastic encased. The one therefore that I have on the outdoor coil, I'm expecting at some point to fail, and I will end up replacing that if possible with a metal one. Since I've had this Dometic Aircon, I've had a look in other people's caravans and motorhomes when opportunity has prevailed itself to sort of check out their Aircons, and by and large, despite the problems that I've experienced with this Aircon, I haven't come across another Aircon that works better than what this one does in terms of heat output, cooling and noise level. So on the basis of that, it is still, in terms of motorhome and caravan use, a good Aircon. One of the things I would sort of mention though is that when I was initially purchasing this, there was a model available which had an inbuilt heater, electric heater, and this was designed for cold climates, because with this Aircon it's a capillary tube Aircon, and one of the downsides of it is that when the temperature starts to get, say, below about 5 degrees, it really struggles to put out heat. And what would normally happen with the Aircon with the inbuilt heating element is that the heating element would come on to supplement the heat output of the Aircon. Whoever I went to in New Zealand, I couldn't find any of them stocking that particular Aircon, but if you are purchasing one of these for your caravan or motorhome, that might be a good option to pursue and see if you can locate one. I don't believe they're particularly are a lot more expensive, but that feature would certainly avoid having to have other clutter in your caravan or motorhome. Now, the modification I've been able to do where I put in resistance in series with the existing thermistor on the outdoor coil, that was only possible because of the fact the outdoor coil really operates over a fairly narrow temperature range, I suspect, probably from -2 to about +4. So I only needed to actually have that thermistor operating correctly in that temperature range, and from the way those two curves ended up in the Excel spreadsheet, you can see I pretty much managed to do that. With the indoor coil, it really has the same function, but in addition it also checks the temperature of the coil, make sure it's above indoor ambient temperature with the rim sensor before it switches on the fan. So when you've got it in heating mode, as it's coming up to temperature, it doesn't switch the fan on. So that indoor thermistor has a little bit more criticality associated with it, and of course it is operating over a bigger temperature range, so doing what I've done would have some issues associated with it. The most sensitive or most critical thermistor in the whole unit is the third one, which is the one that detects the room or inside air temperature. What I have found though is that given that that operates over a narrower temperature range, sort of probably from about 5 degrees to sort of 35 degrees, it hasn't had any problems, and so it certainly seems to be the case that when thermistors are subject to wider temperature swings, their longevity is reduced. So that is something to just be aware of in terms of these replacements. One other thing that's perhaps worthy of note is that if you're running this aircon off a generator, and given it's a capillary type aircon, there's a little gotcha which you might want to be aware of. The aircon basically consumes a amount of power that depends on what's called the temperature lift, and what that is the difference between the indoor and the outdoor temperature that you're trying to achieve. So for example, if it's a 20 degrees Celsius day outside and you're trying to raise the temperature to 25, that's a 5 degree lift. If the temperature outside is 5 degrees and you're trying to raise it to 25 degrees, you've got a 20 degree lift. Now it's a bit counterintuitive, but what will happen is that when the lift temperature is smaller, the aircon will consume more power, and you might sort of think, well, the aircon actually has more work to do when there's a bigger temperature difference, why doesn't it use more power then? In that case it will actually use less power, and as sort of a ballpark figure, if you're sort of at that 5 degree lift and you're in heating mode, the aircon might use 1350 watts, and if you have got the 20 degree lift, it's probably going to use about 1100 to 1150 watts. That is just a function of the operation of a capillary tube aircon, and of course the reality of this is that when you have a small temperature lift, the 5 degrees, while it uses more power, it will get the inside of the motorhome up to temperature quicker because it's pumping out more heat, and so it will spend more time off. So you're not going to go through in total any more power than when there's a 20 degree lift, but it will just struggle a bit more with that higher lift temperature. And that's something which I've come across with using a 1.8 kilowatt generator. When you are in those low lift scenarios, whether it's cooling or heating, particularly so with heating, because it does use a bit more power in that scenario, the aircon, you possibly will have the generator trip out. So the last thing I'll cover off, which I mentioned earlier in the video, is the beta of the thermistor, which is the how aggressive that curve is on the exponential characteristic of the thermistor. We've already seen with the outdoor unit that the beta there appears to be 3950, and I don't actually know what the indoor unit is supposed to be, but I suspect that is also a 5 kilo ohm at 25 degrees Celsius 3950 beta thermistor. The indoor unit, which I have never had to replace, I did get a data sheet from somebody at Dometic, and it would appear, based on that data sheet and my own calculations which I've done in an Excel spreadsheet, that the beta that I calculate for that is 3450, and the beta which I have on the data sheet lists 3470. Now that's a bit of an unusual beta that I've not seen previously with thermistors. So if you do have the room thermistor fail, I think you're probably in a world of guano trying to get a replacement one. But what I'll do after this video is I'll leave up a still picture which shows the data sheet that I got sent for the what I believe is the room or inside temperature thermistor, and I wish you good luck with that. I think that pretty much sums up the end of this video, and hopefully this has been helpful.